Hi, I'm Ellie Pinchers, an Education Officer here at the Royal Meteorological Society. In this series of short films, we're going to be covering some of the background information that teachers may find useful if they're teaching weather and climate at secondary level, and specifically if they're using our Weather and Climate teaching guide with the accompanying classroom resources, which can be found on our website Metlink. There's links in the text below. In this film, I'll be looking at the changing global climate. The climate has always changed, as we saw in Chapter 6, Past Climate Change. However, in the last couple of hundred years, it has been changing rapidly because of the effects people have had on the climate system. In 2022, the climate was around 1.1 degrees Celsius warmer than pre-industrial times. The Intergovernmental Panel on Climate Change states that all the climate change we've seen since the Industrial Revolution has been due to human activities. Over 99% of scientists are in agreement with this. As the climate changes, so does the weather. On the whole, in a warmer climate, you'd expect more warm days and fewer cold days. It doesn't mean that cold days don't happen, they just happen less frequently. Ultimately, the Earth's climate is determined by the balance between the amount of energy we get in from the sun and the amount of energy that the Earth loses back to space. If we get more energy than we lose, the Earth warms up. And that's true at the moment. It's a bit more complicated than this though. Firstly, because the energy can take different forms, light, heat and ultraviolet. And secondly, because there are many interacting processes going on within the Earth's climate systems, the atmosphere, the oceans, biosphere and the land. People have caused the climate to change through changing the proportion of greenhouse gases in the atmosphere. There are many definitions of global warming and climate change. We define global warming as the long-term heating of the Earth's surface since the pre-industrial period due to human activities. Climate change is any large-scale, long-term shift in the Earth's weather patterns. Climate change can be due to global warming, but it also can be due to natural factors. This was the case when we look at the time periods before the Industrial Revolution. Greenhouse gas molecules absorb long wavelength heat, but not light or short wavelength heat. This is crucial because it means they don't stop the sun's light and heat getting in through the atmosphere, but they do absorb the heat leaving the surface of the Earth. Each molecule absorbs some of the rising heat, which warms the molecule up, which then in turn emits the heat in all directions. So the heat that was originally rising towards space is now heading in all directions through the atmosphere. This happens again and again with many greenhouse gas molecules, and the net effect is that the most of the heat ends up travelling back down to warm the surface again, rather than being lost to space. There is a common misconception that the greenhouse gases absorb the sun's energy. This, as we've just looked at, is not true. They absorb the Earth's heat, with the exception to ozone in the stratosphere, which absorbs the sun's ultraviolet or UV radiation. The greenhouse effect is a natural process, and without it, the Earth would be 33 degrees colder. Another misconception can be seen in diagrams that suggest there is a layer of greenhouse gases high up in the atmosphere, a bit like the ozone layer. This is incorrect, as greenhouse gases are what we call well mixed in the atmosphere, and their concentration is actually highest at the ground level. Temperatures in 2023 were just over 1.1 degrees Celsius warmer than pre-industrial average. Ed Hawkins' climate spiral here illustrates really nicely how the average temperature of the Earth has changed since 1850. The rings get progressively further out, but also the year-to-year variations of the weather are shown. Even in a warmer climate, you sometimes get a cooler year or month. Another way of looking at this is the more traditional graphs, like this one, which shows the global temperatures since the last glacial maximum, which is the last time we had a globally cold period in the current ice age. You can see the Earth warms naturally from about 15,000 years ago. Then the global mean temperatures remained remarkably constant for thousands of years, until it started warming again recently. It's probably worth pointing out the change in the scale on the x-axis at 1,000 years before present. So the current warming is actually much faster than it was 15,000 years ago, even though the gradient of the line looks the same. Constructing this graph, published in 2021, was a remarkable piece of work. as most of the information it contains comes from times before we had thermometers or satellites to record the temperature of the atmosphere. To get the data, scientists from a wide range of different fields look at what they call proxy temperature records. These are things that don't record temperature directly, but which we know are affected by the temperature in a way we understand. One example would be the chemical composition of air trapped in tiny bubbles in ancient ice. Some trees, depending on the species and where they are growing, grow better in warmer temperatures, so by looking at the tree rings of ancient trees, or preserved wood, and carbon dating it to get the age, we can see how much a tree grew each year and deduce what the temperature was. Which plants dominate an ecosystem is also affected by the temperature. They also use the pollen preserved in lake sediments as another of these proxy temperature records. The preserved shells of tiny sea creatures can give us data too, as can the shapes of preserved leaves. Scientists then use really clever statistical techniques and a lot of computer processing to turn all this data into a global temperature record. We can zoom in on the last couple of hundred years, for which we mostly have reliable thermometer data. The black line on this graph shows that the rate at which the Earth has been warming has been getting faster. It also shows the difference between how much of the Earth has actually warmed, that's the black line, with how much of the Earth's temperature would have changed if people hadn't affected the climate system, that's the bluish area. We are very, very confident that all this recent warming has been down to humans. Looking in more regional detail, the temperature hasn't changed the same everywhere. Most of the warming has occurred in the Arctic, and it has got warmer faster over land than over oceans. There have also been global and local changes in the pattern of rain and snow, cloudiness, windiness, and all other aspects of the weather. This figure from the IPCC, the Intergovernmental Panel of Climate Change, summarises all the evidence for global warming. You can see that it is very diverse. The most important greenhouse gases, in terms of their concentration in the atmosphere, the length of time they remain in the atmosphere, and the warming they produce, are carbon dioxide, CO2, methane, CH4, nitrous oxide, N2O, and CFCs. Water vapour is the dominant greenhouse gas, but the concentration of water vapour in the atmosphere is determined only by the temperature of the atmosphere. You can refer back to chapter 9 for this. So it is a positive feedback mechanism rather than a driver of climate change itself. As the concentrations of other greenhouse gases in the atmosphere increase, the temperature of the atmosphere warms, and so the concentration of water vapour in the atmosphere also rises, enhancing the greenhouse effect. With every degree of air temperature increase, the atmosphere can retain around 7% more water vapour. Carbon dioxide. Even before humans were around, there was a constantly evolving balance of greenhouse gases in the atmosphere. Natural sources, such as respiring animals, the decomposition of organic matter, volcanoes, rock weathering, freshwater outgassing, and ocean atmospheric exchange of gases are balanced by photosynthesis and ocean atmospheric exchange of gases. Humans have added additional sources and sinks, as is summarised by this diagram from the IPCC. More processes could be added to this picture in future, such as carbon capture and storage. CO2 increased from 278 parts per million in 1750 to 420 parts per million in 2023. Most of the fossil fuels CO2 emissions take place in the industrialised countries north of the equator. Consistent with this, the annual average atmospheric CO2 measurement station in the northern hemisphere, shown in the black line on this graph, record higher CO2 concentrations than stations in the southern hemisphere, shown by the red line. As the difference in fossil fuel combustion between the hemispheres has increased, so has the difference in concentrations between measuring stations at the South Pole and Mauna Loa. Because CO2 uptake by photosynthesis occurs only during the growing season, whereas CO2 release by respiration occurs nearly year-round, the greater landmass in the northern hemisphere imparts a characteristic sawtooth seasonal cycle in the atmospheric CO2. Past changes in the atmospheric greenhouse gas concentrations can be determined with very high confidence from polar ice cores. During the 800,000 years prior to 1750, atmospheric CO2 varied from 180 parts per million during glacial periods up to 300 parts per million during interglacial periods. Present-day concentrations of atmospheric CO2 exceed this range. The current rate of CO2 rise in the atmospheric concentrations is unprecedented with respect to higher resolution ice core records of the last 22,000 years. The main human sources of carbon dioxide are land use change, for example deforestation and agriculture, burning fossil fuels like coal, oil and gas for transportation, heating and industrial processes, and cement production for buildings. Atmospheric oxygen is tightly coupled with the global carbon cycle. The burning of fossil fuels removes oxygen from the atmosphere. As a consequence of burning the fossil fuels, atmospheric oxygen levels have been observed to decrease slowly but steadily over the last 20 years. Compared to the atmospheric oxygen content of about 21%, this decrease is very small. However, it provides independent evidence that the rise in CO2 must be due to an oxidation process, that is, fossil fuel combustion and organic carbon oxidation, and it is not caused by volcanic emissions or a warming ocean releasing carbon dioxide into the atmosphere. The atmospheric oxygen measurements also show the north-south concentration oxygen difference. It's higher in the south and mirroring the CO2 north-south concentration difference, as expected from the greater fossil fuel consumption in the northern hemisphere. Methane absorbs infrared radiation more strongly per molecule compared to CO2. On the other hand, the methane turnover time is less than 10 years in the troposphere, much less than CO2. The concentration of methane in the atmosphere has been rising sharply since 2006. The sources of methane at the surface of the Earth include 1. Natural emissions of fossil methane from geological sources such as marine and terrestrial seepages, geothermal vents and mud volcanoes. 2. Emissions caused by leakages from fossil fuel extraction and use. 3. Pyrogenic sources resulting from incomplete burning of fossil fuels and plant biomass from both natural and anthropogenic fires. 4. Biogenic sources including natural emissions predominantly from wetlands, from termites and very small emissions from the ocean. Anthropogenic biogenic emissions come from rice paddy agriculture, ruminant livestock such as cows, landfill, man-made lakes and wetlands and waste treatment. In general, biogenic methane is produced from organic matter under low oxygen conditions by the fermentation process of some microbes. Both fossil fuels and biogenic sources are responsible for the recent increase in methane in the atmosphere. A recent study calculated that fossil fuels have contributed about 12 to 19 teragrams of methane to the atmosphere each year since 2006, compared to 12 to 16 teragrams per year from biogenic resources. At the same time, emissions from biomass burning decreased by 4 to 5 teragrams per year. Let's take another opportunity to address another misconception, which is that greenhouse gases have a local effect. In other words, if a country emits a lot of greenhouse gases, it will suffer the biggest impacts. This isn't true. Most greenhouse gases are long-lived, meaning they stay in the atmosphere for a long time and get well mixed, at least through the hemisphere they are emitted in. Local emissions have a global impact, and this links with the concept of climate justice. This figure shows the current global annual average flows of electromagnetic and other energy. The number shows the movement of energy in watts per metre squared and their uncertainty in brackets. The income of solar energy at the top of the Earth's atmosphere is 340 watts per metre squared, some of which is scattered back to space by clouds, the atmosphere or the surface. This adds up to about 100 watts per metre squared. The rest is absorbed within the atmosphere. The amount of energy absorbed by the surface determines its temperature, which is currently about 50 degrees C, which in turn determines the amount of energy emitted back by the surface, about 398 watts per metre squared. Water at the surface evaporates, which requires energy, and moves into the atmosphere where it condenses into water droplets or forms ice crystals, releasing latent heat. This transports energy from the surface into the atmosphere. Conduction and convection also move heat from the surface to the atmosphere. Most of the heat emitted by the surface is absorbed and re-emitted by gases in the atmosphere rather than escaping back to space. This is the greenhouse effect that we went through earlier. The heat energy emitted to space, 239 watts per metre squared, together with the reflected solar energy, approximately balances the incoming solar radiation. Critically, the type of solar energy entering the atmosphere, ultraviolet, light and shortwave heat radiation, is different to the longer wavelength heat radiation emitted by the Earth's surface, because the Earth is cooler than the Sun. This means that the processes operating on the incoming and outgoing energy can be very different. Since 1950, the amount of solar energy reaching the surface has been changing. Until the 1980s, it was decreasing or dimming because of an increase in atmospheric pollutants called aerosols. An aerosol is a colloid of either a solid or a liquid suspended in the air, and some of these cause the atmosphere to scatter more sunlight back to space and can also make clouds more reflective by increasing the number of water droplets in the clouds. Since then, national and international legislation has reduced the amount of aerosols, which has increased the amount of solar radiation reaching the surface in some places. Overall, human activities are affecting the Earth's energy balance in a number of ways. Number 1, we're changing the emissions and resulting atmospheric concentrations of greenhouse gases, such as carbon dioxide, which reduce the amount of heat which escapes to space through the greenhouse effect. Number 2, we're changing the emissions and resulting atmospheric concentrations of aerosols which reflect and absorb the sun's radiation. Number 3, we're changing land surface properties which affect reflection, conduction and evaporation, for example by deforestation and increased urbanisation. The result of all these activities is that the sum of energy leaving the top of the atmosphere is less than the energy entering it. The imbalance is estimated to be about 0.6 watts per metre squared. Most of this excess energy is absorbed by the surface, mainly by the ocean, causing the observed increase in temperatures in the lower atmosphere and oceans.